So my name is Guilherme, and I am a second-year PhD student at Universidade de São Paulo in Brazil. And the name of my presentation is The Fragments of an Ancient Dwarf Galaxy, which I hope will make sense by the end of the talk. So I would like to begin by recalling the hierarchical assembly of galaxies, and in which galaxies such as our Milky Way, they grow in size by accretion of small dwarf galaxies of various masses. And in this simulation, which is more than 15 years old now, we can see that when these stars fall in this gravitational potential similar to that of the Milky Way, many of these dwarf galaxies can be still recognized from their spatial distributions as they form these elongated structures that we call stellar streams. However, others will be completely mixed with the Milky Way. So in order to find these accreted dwarf galaxies that no longer show any cohesive structure in their spatial distribution, a very common approach is to look for their distribution in integrals of motion space. So in this figure, I have orbital energy versus angular momentum space, and you can see that in this figure, each star with a different color come from a different progenitor. And you can see that independently of their spatial distribution, these stars, they clump in this parameter space. So this is a very simple idea, I guess. Everybody can understand the conservative quantities. However, this is a very powerful tool nonetheless. And people have utilized this strategy for quite some time now. This is the first kinematically cohesive group of stars that have been found using this methodology in a paper by Helmi and collaborators back in the 90s. I was just a little kid then. And you can see in this angular momentum space, these stars, this group of stars segregated in this plot, these are now called the Helmi strings. And one thing that I would like to call your attention to is that, unfortunately, in order for us to calculate these quantities, it is necessary to have full phase space information. Crucially, we need the precise distances and also radial velocities. Well, fortunately to us, we live in the era of the large-scale spectroscopic surveys as well in the Gaia era. So people have gone ahead have applied this methodology to larger samples of stars in the halo, and this is just quite a good summary of this situation right now. To the left, we can see, for example, the Gaia sausage Enceladus in the middle of this panel, and to the right, we can see, for example, the presence of the Sagittarius string in this energy versus angular momentum space. And indeed, my group and I have also kind of played this game. And in a paper published a few months ago, we analyzed the orbits of very metal-poor stars. And the idea at the time was that groups of very metal-poor stars are for low-mass dwarf galaxies accreted by our Milky Way in the past, such as, for example, maybe ultra-faint dwarf galaxies. And well, another aspect or a byproduct of this analysis was that we were also able to associate several very metal-poor stars with major halo substructures that I had shown to you just in the previous slide. For example, here in the middle, we have, again, the Gaia sausage Enceladus in this red color or something. And also, we can also see the presence of, again of the Helmi strings. And well, another thing that we tried to do at the time was to associate our process-enhanced stars to these found substructures. And these are represented with symbols with green edges in this figure. And surprisingly to us, we were able to associate several R-process enhanced stars. These are elements created, for example, in neutron-star mergers. We were able to associate several of these objects with the Helmi string. And actually, we were not the first ones to notice that. Back in 2010, Roder et al. Were analyzed or followed up with high-resolution spectroscopy several member stars of this substructure, and they ended up noticing that, indeed, some of their stars that they were observing were R-process enhanced. So, but even though this is not something new in the literature, this is a very nice confirmation that, indeed, the stars or the Helmi string is associated with this kind of R-process enhanced stars. This is particularly important given that now we have Gaia data. And almost at the same time, so actually this leads us to the first big question. What about other stars from the Helmi string? Are they also R-process enhanced? And almost at the same time that we published this paper, another article hit the archive by Aguado et al. And in this paper, these authors analyzed the chemical abundance patterns of stars from the Helmi string. And most notably, they also analyzed, in particular, chemical elements associated with the alpha process, here represented, for example, by magnesium. And in this plot, there's also another important feature is that one thing that I would like to call your attention is that stars from the Helmi string span a very large range of metallicities. So this is quite important because this is indeed what is expected to be found in the remnants of an accreted satellite or an accreted dwarf galaxy that has experienced extended star formation history. However, one aspect of this analysis that these authors proposed was that stars from this substructure, from the Helmi strings, were following a similar sequence in this chemical abundance space to that of small dwarf or satellite dwarf galaxies of the Milky Way. In particular, they suggested that stars from the Helmi string were following a similar sequence as the sculptor dwarf spheroidal galaxy, which is represented in this figure by the red dots. And unfortunately, these authors only analyzed the stars of very low metal abundances. As you can see, there is only a single object with metallicity above -1.5. So the second big question that I would like to address was that what about if we, or what would happen if we extended the metallicity range of stars known in the Helmi strings with chemical abundance information derived from the analysis of high resolution spectroscopy? So, and this is exactly the point where GALAH comes in. And in this work, or what we did, and in order to answer or to approach these questions, was to try and select member stars of the Helmi strings in GALAH DR3 in combination with Gaia DR3. And these are just the selection criteria that we utilized. These are selection criteria that had been previously published in the literature. And indeed, we were able to find 8 new members of the Helmi string with chemical abundance information. And you can see that in these figures, these are the star symbols that are in both panels. And one interesting fact or an important feature was that we ended up noticing that by application of these selection criteria that were published in the literature, we were able to recover the distribution of Helmi string stars that we had previously found in that other paper that I mentioned to you. So this is an example of that in the energy versus angular momentum space. And you can see that these stars are distributed within this magenta ellipses in every single one of those panels, which are the selection that we had found previously. So indeed, this is a very good sign that we are selecting true members of this substructure. And then with this confidence, we can move towards analyzing the chemical abundance information. And well, let's start with the first big question that we had was regarding the neutron capture elements. To the left, we have europium over iron versus Fe on H. Fe on H, of course, a proxy for metallicity. And to the right, we have barium over europium versus metallicity, in which barium is a representative of neutron capture elements produced by this low neutron capture process. And not only we can see that indeed stars from the Helmi strings, which are the which are the cyan points in these figures, they have an excess of europium in comparison to the solar abundances, but they also have an excess of europium in comparison to the barium abundances. What this means is that stars from the Helmi strings indeed have been enriched in neutron capture elements predominantly via the R process, as previously suggested in the paper by Roder et al. And we can confirm by adding much more stars, a few more stars to their analysis. But another aspect of this analysis was that we were also able to analyze the alpha elements with data from GALAH. And indeed, stars from GALAH are able to tell us that we can, with data from GALAH, we were able to extend the metallicity interval for stars known in the Helmi strings with chemical abundance information for high resolution data up to -1 in metallicity approximately. And you can see that the inclusion of the data from GALAH in this figure, this is magnesium over iron versus metallicity once again, we can see that indeed we can confirm that stars or this stars from the Helmi strings, for the Helmi string, follow this sequence similar, indeed, very similar to dwarf spheroidal galaxies or dwarf satellite galaxies of the Milky Way. In particular, they follow a very similar sequence to that of the sculptor dwarf spheroidal galaxy. And well, the main takeaway message here is that I would say that given the accumulated evidence from kinematics and dynamics, as well as from chemical abundances, we can assert with a very good degree of confidence that indeed the Helmi strings are the fragments of an ancient dwarf galaxy that has been accreted by the Milky Way in the past. I'll leave you with my main results and some takeaway messages, and I'll be happy to answer your questions now. Thank you so much.
Thank you very much. That was a very interesting talk. Do we have questions? So I'll go ahead and start with one. So it's very interesting that the abundances match up so closely with Sculptor, but maybe Sven might be able to weigh in on this. How much do we trust the GALAH abundances at metallicities of -1.5 and -2? I'm just not sure how much confidence I would put in the magnesium, for instance, at these very low metallicities. It is very interesting that they tend to follow Sculptor, but.
Yeah, this is a very good question. Indeed, if we look, I would not be really concerned about that because, well, we did everything that we could in order to eliminate any possible spurious chemical abundance information, for example, by limiting the signal to noise ratio, as well as, of course, doing the standard filtering from quality flags. But you can see that stars from this work that we selected from GALAH, there are only 2 of them that are below -1.5 or -2. So yeah, I would trust the abundances of the stars. So even if we remove these stars, the qualitative conclusion would remain is that these stars follow this kind of a declining sequence in this chemical abundance space. So this is a very important question actually, but I would say that these results are robust against that, even if we eliminate those stars. So does that answer the question?
Yeah. Do you have any
okay,
additional questions? All right.
Sorry, but I'm not sure if I can raise my hand, but I just wanted to say great work. It's also great that like in the paper you actually have the spectra plotted. Always good. So it's really nice to see actually the European lines and nickel, and so that it's a clear detection, right? So that makes me also confident in what you show here. Very good work.
Oh, that's good to know. Thank you so much.